If you have the function f of x equal to x squared minus 1 divided by x minus 1, then we cannot calculate it for x equal to 1, because then we get 0 divided by 0. And that's not defined. However, if we put in values very close to 1, then we can calculate it. So for example, if I put in 0.9, I will get this. So I get the value is 1.9. And if I put in values closer and closer to 1, calculating in the same way, I will see that this becomes, if I put in 0.999, I will get 1.999. So we can see that this will approach 2 when I get closer and closer to 1. I can also approach x equal to 1 from the other direction. Here we have approached 1 from the left to the right. I can also approach 1 from right to the left. And if I calculate this, I get this, and I'll get the answer 2.1. In a similar way, I can get closer and closer to 1. And so here you see that if I get closer and closer to 1, I get closer and closer to 2. So we see, although we cannot calculate exactly what the value is for f of 1, we can calculate f of x when x is close to 1. And then we see that we get closer and closer to 2. And that we say as the limit of the function f of x when x approaches 1 equals 2. So although we never get exactly 2, but when we approach 1 for the function, it gets closer and closer to 2. So the limit of the function is 2. More generally, we say that the limit of the function f of x when x approaches a is equal to some number b. So the arrow here should be understood as when x approaches a. In this case, we can actually see that the function will approach 2 in another way. So if you write this as this, using the difference of squares, then we see that we can shorten this, and that this remains. And we see that this one approaches 2 when x approaches 1. Let us consider this function instead. Here we want to find out what happens to the function when x becomes indefinitely large. We see that if we put in larger and larger numbers, for example like this, we see that the function gets closer and closer to 0. So although we never can get to infinity, we say that the limit of the function when x approaches infinity is equal to 0. We can also approach infinity in the other direction, if we go to infinitely negative. For example like this. We see that also in this case the function approaches 0. So when the function approaches minus infinity, the function goes to 0. So we say that the limit of the function when x goes to minus infinity is equal to 0. Consider again this function. We see that we cannot calculate the function for 0, because then we get 1 divided by 0, and that's not defined. However, we can calculate the function for x arbitrarily close to 0. So if you take smaller and smaller values, for example like this, then we see that the function approaches infinity, because this can become as large as we like. However, we cannot write like this. Because if we now look at what happens when we approach 0 from the other direction, for example like this, we see that the function approaches minus infinity. So we see that when x goes to 0, it approaches infinity if we go from the right. That is, if we come closer and closer to 0 on the x-axis from the right. However, it goes to minus infinity when we approaches x from the left. And since we have two different limits when x goes to 0 depending on which direction, we say that the function does not have a limit. However, we can introduce the following notation. If we write like this means that we go x goes to 0 from the right. So we go from the positive side. Then this will go to infinity, as we have seen here. And we can also write if x goes to 0 from the left, from the negative side, it goes to minus infinity. And since these two limits are not the same, depending if it comes from the right or from the left, it has no limit when x goes to 0. And we can see that clearly here. If we go from the right, you see that the function approaches infinity. If we come from the left, the function approaches minus infinity when x goes to 0. More generally, if the limit of the function when x goes to a from the right is not equal to the limit of the function when x goes to a from the left, then we say that the limit of the function when x goes to a is undefined, since these two limits are different. However, we can still talk about the left and right limit like this, but they are not equal. If we instead look at this function, then there do in fact exist a limit of this function when x goes to 0, because no matter if we go from right or left, this will be infinity. And that we can see easily by drawing the graph. So we see that the function goes to infinity both if we come from the left or from the right, approaching 0. If you want to calculate the limit of a function like this, for example when x goes to some number not 0 or infinity, let's say 2, then we see that nothing particular happens with the function when we put in 2. So in this case we can just calculate for x equal to 2. So this is a half. So we can write here limit of 1 over x when x goes to 2 is just a half. Assume that we have two functions, and assume that the limit of the two functions when x goes to a are both equal to infinity. Then we cannot say directly what the limit of this will be, because this will be infinity minus infinity. And what this is depends on exactly how fast these two go to infinity. Let's look at an example of this. Assume, for example, that f of x is equal to x squared and g of x is equal to x. Then we see that f of x and g of x both go to infinity when x goes to infinity. So the limit of the difference of the two functions will be the limit of this function. But this function goes to plus infinity when x goes to infinity, because x squared grows much faster than x. So in this case we have infinity minus infinity. But if we switch around and take g of x first, then we instead have this, the limit of x minus x squared. Here this goes to minus infinity, because this grows much faster than this one. So we cannot say directly, if you have an expression like this, infinity minus infinity, what it would be, because it depends on exactly how fast this function goes to infinity. And that's also the case, for example, if you have a division. Here we see that this one will go to 0, while this one will go to infinity, because this is just 1 over x and this is just x. So you see in both cases we have that it goes to infinity divided by infinity, but what the value of this is depends on how fast they approach infinity. So we cannot say directly what something like this would mean. So in that case we have to examine more closely the functions. If you have a function, for example, as 2 plus 1 over x, then we see that the graph looks like this. And let us also put in the line y equals to 2. Then we see we get this orange line here. If you now zoom out, we will see that the function approaches 2 when x goes to infinity. The limit of this function is 2 when x goes to infinity. And in the same in the other direction. Also the limit of the function is 2 when x goes to minus infinity. So we can find asymptotes, which we have talked about before, by looking at limits. If we instead look at the function like this, then we see that have this graph. And let us put in the straight line x equal to 2. Then we see that the function approaches the blue line when x goes to 2. So we see that we have a vertical asymptote here for x equal to 2. So you can find vertical and horizontal asymptotes by looking at limits of functions. And if you have a function like this, x squared plus 1 divided by x minus 1, for example, you also have asymptotes. And the asymptote in this case will be this line, x plus 1. Because if you zoom out, you see that our function approaches this straight line when x goes to plus and minus infinity. So again, we can investigate asymptotes by looking at limits of functions.